Welcome to lecture number 34. So, today we will going to discuss the excited state proton transfer. To start with, let me tell you the normal proton transfer in the ground state. So, if you have a molecule which is denoted by Ha, that H, which is a proton, can be donated either to the solvent or to some other molecule to make it A minus and H plus, right. Let me write this, then it will be much more clear. So, you have a molecule Ha and that can be dissociated to A minus plus H plus, and if I denote this equilibrium constant is Ka, then then this Ka can be written as concentration of H plus, concentration of A minus divided by this we know, right, concentration of Ha, that is it. So, taking log on at both the side and again one minus sign. So, this will be minus log Ka, and in this part will be minus log hydrogen ion concentration, which is nothing but the pH, and then minus log A minus by Ha concentration. So, taking log, I can write log minus log Ka is equal to minus log hydrogen ion concentration plus minus log concentration of A minus divided by concentration of Ha. So, note that this concentration of A minus and concentration of Ha is at the equilibrium, this is not the original concentration. So, this is nothing but pKa equal to pH minus log concentration of A minus divided by concentration of Ha. Now, if I consider that this Ha is associated with some chromophore, right, or in the other hand this Ha has a specific absorption spectra and A minus has a different absorption spectra, then it is straightforward to measure the concentration of A minus and Ha by the spectrophotometric method, and one will get okay, for example, if this is the absorption spectra of Ha, this is the absorption spectra of Ha. Now, if you increase the pH of the medium, more and more Ha will be converted to A minus. So, here I am plotting the absorbance or OD, whatever you want, this is the same thing, and here is my wavelength, right. So, once you increase the pH of the medium, then more and more Ha will form A minus, and if A minus is having a completely different type of absorption, let us say like this way, the A minus absorption is something like this. Then what we will going to see that formation of A minus at the expense of Ha. So, Ha will decrease and A minus will increase. Individually, if you know these epsilon values, then from there you will be able to calculate what is the concentration. So, initially if this was Ha, then this Ha will decrease and there is some formation of this A minus. If you increase the pH more, then it will be like this and so on. And here this two H A and A minus are well separated, like they are not overlapping with each other. If they are overlapping with each other, you have to do a little bit of more calculations to get the relative concentration of HA and A minus as a function of pH, and once you know that, you will get this part, and you already know the pH, and you will be able to calculate the pKa. Right. The lower the value of pKa, the higher is the acidity of that substance. Suppose this HA has a pKa of 6, that means it is a weak acid. If the pKa of HA is around 9, that is not at all acid. I mean, it cannot donate the proton to water, right. If the pKa of this HA is, let us say 1, that means a strong acid, right. For some molecule, that is what our discussion is all about. For some molecule, it has been seen that the molecule has a very low acidity in normal condition, but once you excite the molecule by photoirradiation, right, the excited state of the molecule become very strongly acidic in nature. So, it can readily donate the proton, right. So, for example, this molecule if you take, what is this molecule? This is 2-naphthol. This 2-naphthol. The pKa of this molecule is about 9.2. Obviously, this proton is not labile in the ground state. So, acidity is very low, right. However, if you excite this molecule using 270 nanometer, 280 nanometer light, right, around 280 nanometer, if you shine 280 nanometer UV light, then the pKa of this molecule drastically reduce to 2.0. So, I say that this pKa star, because it is excited state phenomena, it is under the photoirradiation, that means the molecule is now at the excited state, not in the ground state. So, in that case the pKa star is 2, pKa star 2 means is highly acidic, but this highly acidic nature of this molecule is only present when the molecule is in the excited state. The molecule when it is in its ground state, then the molecule is not highly acidic in the nature, right. For example, it could be completely different itself. For example, let us see this molecule. This molecule is acridine, right. So, in this molecule the pKa in the ground state is 5.1. So, it is a moderately acidic molecule, right. However, in the excited state, if you shine light, right, in the excited state the pKa turns out to be 10.6. That means, under photoexcitation these molecules become a strong base. It was 5.1 in the ground state, but in the excited state it is 10.6. So, you see the change of this acidity of this molecule under photoexcitation. The case, right, where you see such kind of situation that pKa star is much lower compared to the pKa, then it is possible that if you have a base sitting next to this molecule HA in the ground state, the proton could not be transferred because it is not favorable from HA. Now, let me write this HA plus B. So, I am going to have A minus plus BH plus. So, formation of this conjugate base or the conjugate acid of this base B, right, this is not favorable in the ground state, but because the pKa is very high, right, for this HA. But once you excite this molecule you put this molecule HA in the excited state, immediately this takes place. So, leaving this molecule in the excited state. So, that means the proton transfer from HA to B is taking place in such kind of cases only in the excited state, and this is known as excited state proton transfer. In short form, people call this as ESPT. Now, if it is within the same molecule, like the one part of the molecule is proton donor and the other part of the molecule is proton acceptor, then it is known as excited state intramolecular proton transfer and denoted as ESIPT. But we will not going to discuss this one in this course, we will only going to discuss this part. Okay. Now, let me draw this energy diagram of this excited state proton transfer. So, in this case what you can see is that this is my HA, and upon excitation it form HA star. So, this is my H nu absorption. If this proton can be donated to somebody, then something else, but otherwise it will come back to the ground state and it will going to give you the HA emission in presence of the acceptor of the proton, right, then only it will going to give to somebody. If you just take this HA in the gaseous state alone and you are exciting, I mean it will not be able to donate the proton to anybody. So, it will not going to donate, something has to be there to accept it, right. Typically, if you dissolve it in water, then water will be H3O plus, then it is it will form the conjugate acid of the water. So, in that case then HA star will be able to donate its proton to form the A minus. And if I now draw this A minus, it could be anything like this is my A minus energy state, here is ground state, here is A minus star, right. So, this proton can be donated from the HA star to A minus star, and then correspondingly A minus emission will be observed. So, what you will get here is the A minus emission. That is what you will going to see in the experiment, right. So, in the experiment what you will see, in this case you are not going to record the absorption spectra, because absorption is a ground state phenomena. Here you are going to record the fluorescence or emission spectra, because the emission is the excited state phenomena. Okay. So, you will going to record the emission spectra, and let me draw a typical emission spectra of such kind of molecule. What you will going to see is when there is no one to accept the proton or the pK star value is very high, right, it is not possible to donate the proton, then you will only going to see the emission spectra coming out from the HA, right. So, this is my intensity of fluorescence and here is your lambda emission. So, this is specifically for HA molecule, right. But if somebody is there, then this fluorescence intensity will decrease and another band will come, which is by the A minus star, right. So, this will decrease and another band will come because of A minus. Right. If you have more acceptor present for this proton, then obviously this band will increase and decrease. It is clear from this diagram that the relative concentration of HA star and A minus is somehow related to this intensity, because this is my A minus, right, in the excited state, right. I should write here star. So, this is A minus star. So, fluorescence intensity is more, that means the number of A minus star is more, fluorescence intensity less means number of A minus star in that solution, right, is less. HA, this fluorescence intensity of this band is more, means number of H A star is more and vice versa, right. So, if I just simply write this equilibrium, this part, let me write it. So, here my equation is H A star is converting to A minus star plus H plus, right. You see this equation and this equation is very similar equation, or this is only in the ground state, but that one is in the excited state. So, I can simply write this equilibrium constant K, but as it is in the excited state. So, it is I will write the K A star, right. So, I can simply write that K A star is equal to concentration of A minus star to concentration of H plus divided by concentration of H A star. Again, to tell you that these concentrations are equilibrium concentrations. So, if I take a negative logarithm of each side, so I will get P K A star equal to P H, right. Here obviously no excited state, is just a hydrogen concentration, minus log of A minus star divided by H A star, right. Now, you can tell that okay, I know this emission intensity as I showed here. So, this has to be related with the concentration. Concentration is more, emission intensity more. So, concentration of A minus is less, emission intensity is less. So, I can immediately put this this intensity ratio as the ratio I wrote over here, but there will be problem, because fluorescence intensity does depends on the concentration, but it also depends on its own radiative and non-radiative pathway, right. There is no guarantee that the nature of the radiative and non-radiative pathway for H A and A minus they are exactly same. In other words, the quantum yield of H A and A minus are exactly same. If not, I cannot directly compare the intensity with the concentration. So, I cannot write. It was much easier for me in case of absorption, because earlier I know that absorption spectra, but if you know the quantum yield, then probably it is okay. You have to convert this concentration to the by taking into account the appropriate values of quantum yield for the H A and A minus. However, we can do another simpler thing to get this value of P K star, right, which is being done or followed universally. For example, if I now may draw this excited state proton transfer by such kind of a diagram. Let us see this one. So, here is my ground state, right, and this is your H A and this is your A minus plus H plus, and this is let us say delta H, the energy difference between these two. In the ground state, you see this barrier is very high, right. So, naturally the pKa value is really high, right. It is not a very good proton donor. The excited state is something like this. Something like this, okay. And so, here is my state, this is my H A star, right. this is my H A star, and let us say you have used H nu prime. This H nu prime or nu prime is the maxima of the frequency for this absorption, right. So, you can excite the system from here to here, and this one this energy difference, let us say delta H star, right. Then from here to here this will be your emission, because if this A minus will form, then A minus from the excited state will come to the A minus ground state, and then it will take the proton back to form the HA. So, this is my full that diagram of this proton transfer. So, this one is A minus star. So, here is my HA star, this is HA, here is A minus star, and here is A minus, right. These are the four thing I have. Now, from this diagram I can easily write two things. One is H A, no sorry, the delta H star plus H nu prime, right, and that also has to be multiplied by the Avogadro number. So, I can write, let me write here delta H star plus H nu prime multiplied by Avogadro number, right. That should be equal to, if this emission is H nu double prime, then Avogadro number H nu double prime, that is from energy from here to here plus here to here, this is equal to here to here plus here to here. So, to make it more understandable, let me draw this line also, right. So, this will be equal to delta H plus H nu double prime into Avogadro number. I can write this. So, now let me rearrange Na H nu double prime minus nu prime is equal to delta H star minus delta H. Now, this delta H can be written as delta G if I consider the change in entropy in both the case are same, right. So, this can be written as delta G star minus delta G under the assumption that delta S star is equal to delta S, right, for ionization, and this is a valid assumption, right. It is just whether the ionization is taking place in the ground state or in the excited state, the change the delta S, the change in entropy should be similar, right, it should not be very different, right? So, ionization, right, and I know what that delta G is equal to 2.303 RT pKa, right, RT pKa. So, here I plug in these things. So, Na H nu double prime minus nu prime is equal to 2.303 RT pK star, because it is in the excited state, minus 2.303 RT pK because it is in the ground state, right. So, I can simply write that pK A star minus pKa is equal to Avogadro number, Planck constant, nu double bar minus nu bar. This nu double bar is the emission frequency of the A minus, and this nu bar is my absorption frequency of this HA, right. I am exciting over here. In this case, excitation and emission is same. I am not just considering here H nu bar absorption or excitation is same under this condition. Okay. If they are not same, then probably you can excite to some other value, but so strictly speaking here I have only one level. So, if you excite some other higher vibration level, then this is actually the emission, right, is actually the emission. For the simplicity, for the simple model, I assume it to be the exactly same as the absorption and emission, but if you consider Stokes shift, then better to write this as a emission, right. So, H nu prime is a emission maxima of HA, and this is emission maxima of A minus, right. So, then this will be equal to Avogadro number H nu double prime by nu prime by 2.303 RT. That is it. So, if I know the pKa in the ground state, then I can readily calculate the pKa star in the excited state, provided I know what is the emission maxima of this HA, what is the emission maxima of this A minus, and these are other things are the constant term. Let's say for example, I should give you example, the for this 2-naphthol, right, I showed, right, A H star emission is at 360 nanometer, right, and A minus star emission is at 415 nanometer. So, from here I can calculate nu bar equal to 8.33 to 10 to the power 14 second inverse is interconvertible, and from here nu double prime is equal to 7.23 into 10 to the power 14 second inverse. If I know already that pK of this molecule is 9.2 in the ground state, right. So, pK is 9.2, then pK star can be calculated from this equation, right, and if you calculate, you will get is around 1.5, right. So, immediately you will get this value. Okay. So, now we should discuss about the rate of this proton transfer. This is that the pK star, right, whether in the excited state the proton is more labile or not, and how to find out, that is what I have done now, right. But I should tell you how we will find out the rate of such kind of reaction, acid proton transfer. Once excited, that means instantaneously you are creating the excited state. So, just of a sudden you are creating a very strong acid, and then it will going to donate its proton, right. And is it possible to follow this reaction with time or not? That we will going to see in our next class. Thank you very much.